I drew a map of Pennsylvania. Pennsylvania is my home state. I also drew on some contours corresponding to temperatures. I just kind of made up this example, 30 degrees, 40, 50, 60, 70. I've rigged it. I'm from what I consider to be the coldest part of the state, and I've made sure that the map represents that. So why do I do this? It lets me set up the following question. So suppose that you are taking a trip around Pennsylvania and having a grand old time kind of riding your bike around here. So the question is, how is your temperature changing with respect to time? So here's the thing. This map here, we're like given temperature as a function of position in two-dimensional space. So like right here, that looks like Scranton or something like that. You're at 50 degrees. Over here by Clearfield, you're at 40 degrees and stuff like that. Philadelphia down here is like at 70 degrees. We gave you, you're given a map here of temperatures. We're showing temperature as a function of position, but really position is a function of time. So if temperature is a function of position, but position is a function of time, then actually underlying all of that, your temperature is a function of time. And so we'd like to know, how is your temperature changing with respect to time if we give you information about temperature as a function of position and your position as a function of time. Okay, so long setup, short answer here. This chain rule for paths, theorem right here, does exactly what we want it to do. So it says here, the derivative with respect to t of f of r of t is equal to the gradient of f evaluated r at t dot product with r prime of t. Where I need to tell you what t, r, and f all are. So t is our parameter. For example, time is probably the easiest way to think of for t here. R is a vector valued function of t. And probably that's, usually corresponds to your position here. And finally, f is a function of multiple variables. So this might be, in our running example, temperature at a given position. So f here is a function is temperature as a function of the position, but r is the position function as a function of time. So f really is a function of time here. We're asking, how does f change with respect to t? And this over here gives us the answer. We take the gradient of f, evaluate at r, and multiply it by, take the dot product with r prime of t. And so let me point out here that this fits our pattern of what we should expect a chain rule to look like, right? So chain rule is take the derivative of the outside function while leaving the inside function alone, multiply it by the derivative of the inside function. So taking the derivative, in quotes, of the outside function is f. Taking the derivative of f is really finding the gradient of f. We leave the inside function alone, we're evaluating that gradient at r of t. The multiplying it by the derivative of the inside function, well, r prime of t is the derivative of the inside function. And then finally, we have to ask the question, well, what do we mean by multiplying? And in this case, it is In this case, it is dot multiplication, the dot product. Let me just point out here one other way to write this. Let's assume that our function is a function of 3 variables here. So the gradient of f would be df partial f partial x, partial f partial y, partial f partial z. Dot product with, if we're writing r as x of t, y of t, z of t, dot product with x prime, y prime, and z prime. And so if we do the dot product, it's this times this plus this times this plus this times this. df dx partial f partial x times dx dt plus partial f partial y times dy dt plus partial f partial z times dz dt. This should look a lot like the chain rule that we did in section 14.4. Let me just highlight the fact that these are partial derivatives and these are normal derivatives because x, y, and z all depend solely on t. And you can prove this basically. This just follows from all of the chain rule stuff that we did in section 14.4. Okay, so this will give us a tool to answer this kind of question. And so here is the specific example we're going to do. Temperature is a function of 3 variables. We're thinking that inside this room, the temperature at point x, y, and z is given by x e to the y over z cubed plus 1, all of that cubed. And then we have a bug. I specifically chose a bug so I can fly around the room and move in 3 dimensions. The bug, the position for the bug as a function of t is given by t squared, t cubed, t minus 1, that vector for t greater than or equal to 0. So the question is, at what rate is the bug's temperature changing at time t is equal to 1? So we'll do this, we'll do this using the chain rule for paths. What do we need here? We'll have to do lots of calculations. Like we'll need the gradient, we'll need some derivatives. Let's get to work on those calculations. So we need the gradient of t. We take the derivative of this with respect to x. E to the y over z cubed, c squared plus 1, all that cubed. Those were all constants, so it's just e to the y over z squared plus 1, all of that cubed. Take the derivative, partial derivative with respect to y. X and the z stuff is constants. The derivative of e to the y will just be e to the y. So x e to the y over z squared plus 1, all of that cubed. And then we'll have to use the quotient rule to do the partial derivative with respect to z. And so the answer just ends up as minus 6x e to the y times z, all of that over z squared plus 1 to the 4th. Okay, so this is the gradient of t. We're being asked about at time t is equal to 1. So r of 1, plug in 1 in here for t. We would get 1. 1 squared is 1, 1 cubed is 1, 1 minus 1 is 0. We also know from our formula we're going to need r prime of t. So r prime of t is going to be 2t, 3t squared, and 1. And let's also plug in r prime of 1 into r prime, and we would get 2, 3, and 1. Okay, so at this point, let's use the chain rule for paths to write down our write down the formula here. So the derivative with respect to the derivative with respect to t of big T of r of little t, evaluate at t is equal to 1, by the chain rule for paths is equal to the gradient of t, plug in r of t, but we're evaluating this at t is equal to 1, so I can just say evaluate this at r is equal to 1, dot product with r prime of 1. Okay, so we should be able to do everything here. R prime of 1 is 2, 3, 1. And when we plug in r of 1, 1, 1, 0, plug in x is 1, y is 1, z is 0. When we make all of those plug-ins, I'm just going to skip the calculations for that. Feel free to check that this is good. The entries are e, e, and 0. So take the dot product of these two vectors. 2e plus 3e plus 0 gives us 5e. So that is an application of the chain rule for paths. It allows us to, it's a nice, this is a nice theorem here, because it takes this kind of question of, how is your temperature change in respect to time as you move through this picture here, and it has a pretty succinct, clear answer for that.